All right, it's my pleasure to introduce our fourth speaker. This is Jacob Cruz.
Hello, everybody. I'll try to make it fun for our last 15 minutes here. And I just want to thank Esri for showing the beautiful state of Wisconsin, where I'm from, as one of the 5 states featured on theCUBE. So thank you. All right, so today I'm hoping to share a little bit about our recent project. It's an ongoing project, so I would love feedback and stuff from everybody. But there's the title, Interactive Web Mapping for Multi-Criteria Assessment of Redistricting Plans. And what I'm going to do is actually kind of start with the more redistricting science side, and then we're going to go into a cartography aspect later that's more of an educational component. So first of all, what is redistricting? It's the process of drawing electoral boundaries. So for example, in the state of Wisconsin, we have 8 representatives in the U.S. House of Representatives. So every 10 years, you take the whole state and you chop it up into 8 districts, 8 contiguous districts that are equal population. And each one of those districts gets to represent 1 representative in the U.S. House of Representatives. And so there's kind of a normative assumption behind that districts should be representing groups of people with shared interests. There's something coherent about the grouping of that. Otherwise, you might just take the top 8 vote getters and just elect them all to the House of Representatives. So there's some sort of sense that there's a community underlying these districts and that these districts capture these communities well. So in the political science literature, this is typically talked about in terms of communities of interest. I know there's the communities of interest piece, which is identifying like very particular communities that we want to make sure are within one district. But more generally, we're just talking about districts as a whole capturing communities of interest, meaning communities that have some commonalities that they might want represented at the, whatever level you have. So. But the thing is, in political redistricting, there's no clear definition of this. There are a couple of proxies people may have seen. This has been really popular in the last 10 years, given all the recent gerrymandering work. But things like compactness, heat maps that kind of aggregate different communities of interest that people drew on maps, split municipalities counts, so saying, hey, how many counties are we splitting while we make these districts? These are all kind of proxies that political scientists have used to try to get at how well are these districts capturing the underlying communities. So, and these are great because they're countable, which is good, but it's unclear if they're really meaningful. If we think of just kind of common sense, intuitive definitions of human communities, these, again, are all proxies, but they don't really seem to indicate what's really happening on the ground in terms of where, how people are actually interacting with each other. So again, this is from the political science perspective, but how might a geographer approach this question? So to answer that, we're going to kind of put on our human mobility analytics hat. That's kind of our bias in our lab. We're a quantitative geospatial data science lab. And so we're kind of look at this through the lens of people interacting in space and time is a great way of talking about communities. It's at the very least, it's a very real sense in which you have communities. So to give a little example, I'm from Madison, Wisconsin, which is kind of right there by the orange in the middle there. It's a little hard to see unless you know what you're looking for. But I spend most of my life kind of in downtown. Maybe I wake up in the morning, I go to campus from my house. I go to the gym after, which is a couple blocks away. Maybe I bike back home after, and then maybe I bike across the isthmus later at night to go to a jazz club or something like that. So that's like 90% of my daily life. 90% of my interactions are with other people in that tightly contained area. Maybe once every 2 weeks, I'll go out and I'll visit my parents who live a little farther out. They live about 30 minutes outside of town. So, we can see I have community with them, but, the interactions are a little less frequent, a little more tenuous. And maybe every 6 months, I go visit Chicago or Milwaukee, which are 2 or 3 hours away, to see a friend or something. And so, there's another sense in which I have community. I'm in a community with these people, but it's much more tenuous because it's much less frequent. And so we're hoping to bring this geographic kind of interaction definition of community into redistricting. And our claim here is that districts that capture how people move are normatively better than districts that don't. And this probably doesn't sound that crazy to anyone in geography, defining community in that way. but it is new to the political science redistricting literature. And so we're happy to kind of be able to get an easy win there, bringing something that's standard for geography and bringing it into a new field where it's very exciting. So diving a bit more into how we actually might measure that, I kind of just gave an example, but if we want to actually quantify community, we need to give a definition to it. And in this case, we came up with this metric called the modularity ratio. If anyone here has worked in community detection, you might be familiar with the term modularity, which looks at kind of the density of connections within one community versus between that community and other communities. And so a more modular district map in this case might have more dense connections within communities than between communities. And so we call that as the ratio. It's a global metric across all districts. It's the sum of intraflows, so flows within districts, divided by the sum of flows between districts. And as the data source, I think some other people here have used this data source as well. It's from SafeGraph. It's basically mobile phones that people carry around with them, and it's some portion of the population. I think it's about 10%. So we scale that to the population level just using some census data. So here's a basic just example to show how we might calculate this modularity ratio metric. So here I've just plotted up 4 different districts, and you can imagine each of those has subgeometries, maybe census block groups. That's what we work with the SafeGraph data, but we're not showing those. We're just showing the district boundaries. So in the black lines, we have intraflows, which are flows of people originating in that district, District A, for example, and ending in District A. So in this example, 7 people move from somewhere within A to another place in A. Then we also have interflows, which is visualized by the white arrows, which would be, for example, the number of people that move from District A to District B. So in that case, that's 1, or from District B to District A, which is 4. So to characterize the degree to which this whole map is capturing communities, we want to do the sum that I mentioned. So on the top there equation, we have the sum of intraflows, which is the sum of all those black arrows, divided by the sum of interflows, which is the sum of all those white arrows. So in this case, we get in this example, we get 1.25. So that's saying this has more dense intraconnections relative to a map that maybe got a score of 1, which would be you have even numbers of interflows and intraflows. So this better captures community than a other district map you might make that had a score of 1. So that kind of brings up the question of how do we compare this? We could look at a given map that a given assembly creates, like for example, for 2020, most state assemblies just approved their district maps and such, or state level governments approved their district maps. But that's not the only thing we care about, because especially a lot of this stuff that we're drawing upon is research that's used in litigation to contest maps, and you want to get a sense of how your map compares to all the maps you could have drawn. And the problem with that is that you can actually draw billions or trillions and trillions of maps for even a given state. In Wisconsin, there's like 4,300 some CBGs, and it's impossibly large, the number of potential valid maps you could make, even while adhering to the constraints laid out in state government to completely draw all those. So what you do instead is you use something like the recombination algorithm, which I have up here. This is from the metric geometry and gerrymandering group. It's a really great algorithm, but basically there are other algorithms like it, but this one is really good at kind of sampling from the total space of valid maps you could make and getting a representative sample. And then we could kind of score a given metric of interest, in our case, the modularity ratio, to see how a given map might compare to the total space. And we'll go into that in a little bit in the interactive cartography portion, but so just to kind of summarize all that, we know right now there are a given number of criteria that are used to evaluate fairness or if a map is gerrymandered or not. And those are frequently compactness, something like the efficiency gap for fairness, preservation of municipal units, adherence to existing boundaries. And we want to add this new measure that really actually gets at the degree to which you capture real underlying communities as measured by human interactions and socialization. So, but the problem is this is a really big space of total solutions, right? You can imagine like it's very common to generate 10 to 15,000 maps for a sampling chain using the recombination algorithm. But you can score all those relatively easily with different software, but it's hard to like make sense of that as a human. So what we wanted to do was to make an interactive web map that would allow people to kind of play around with different maps that you could make to get a sense of what happens when I maximize a map for modularity? What happens to the other criteria we care about? What happens if I maximize a map for compactness? Does that make my modularity worse? Does that, decrease representation across different racial groups, et cetera? So I'm just going to kind of briefly go through these. I just have some slide shots. These we actually made, me and my collaborator Yuhan in our lab made while we were taking Rob Roth's great interactive cartography class at UW-Madison. So, but it is the beta version, I will say. So blame me for any cartographic design problems, not Rob. So the main thing I kind of want to highlight here is that you can see I have two maps pulled up. Those are the maps that are checked near the red number 1. So we have the 2020 currently enacted map on the left side. And you can see those are kind of all nice and neat. It looks like they clearly put some intentionality into following existing boundaries that in fact is actually a rule in Wisconsin. Whereas the one on the right, what we selected for was the max modularity ratio map. And this is not an exhaustive sample. This was kind of preliminary results. But the point is what you can see is if you compare the district boundaries from the map on the right to the map on the left, you could see that the one on the right, those boundaries are they're squiggly, they're all over the place. They don't follow neat straight lines. And that's kind of one of our main takeaways that we wanted to focus on. If you're focusing on trying to really preserve communities, that won't necessarily look the same as if you're trying to preserve municipal splits or compactness or whatever you might choose. So up here, I've just chosen those two maps, but as you can see, you can also choose to highlight, you can pull up the map for max efficiency gap, or another map that was made by the People's Map Commission, which is kind of a nonprofit map to design fair maps, or you could choose a map that maximizes compactness. So again, just trying to get a sense of the trade-offs involved there. Just to highlight some of the other interactive features we put in. So if you look at the red number 2, that's a parallel coordinate plot. What's great about that is for each district, you can see how all the different demographic or metric variables or attributes vary from district to district, and you can kind of compare them between the two maps. For example, if you look at the red letter 3, or the red number 3, that district around that is kind of highlighted. That in that case, I was hovering over that with the mouse, and then that corresponds to the line in the parallel coordinate plot near the red number 4. So again, just kind of making it easier to pick out different districts in there and see, okay, before this district, didn't include the city. I don't know northern Wisconsin super well, but you said maybe Tomahawk was in this district before. Now it's not. Let's see how that changes our demographic makeup of this district or the intraflows of that district. And then just to highlight what we're going to see in the next two screens, at the bottom right, you can see there's these re-express operators, which I'll just briefly show here. So one, you can express the attributes up in the parallel coordinate plot as a proportional symbol map. So here we have visualized the number of Black residents in each district. So you can see in the bottom right, Milwaukee, clearly there's a spatial dimension to that, and this helps you visualize that. We can re-express again in terms of bar charts, and we can even hover over the bar charts again to see those same districts, those same demographic attributes shown at the top. And then finally, just kind of at the bottom of the screen, the text is too small, so I don't expect anyone to read it, but just to give a sense of the sort of text and image descriptions we have to help people make sense of this. So in summary, this is all kind of what you have. Again, we have the contribution of bringing a geographic metric into political science, which hasn't been done before, and to really kind of quantitatively describe community in an actual way rather than just a proximal way. And then on the other hand, we have this interactive web map component that we're working on to help people kind of make sense of the trade-offs of redistricting, since it's a very complex science and there's a lot going on. So with that, I want to acknowledge our funding. And I also want to acknowledge again the metric geometry and gerrymandering group, which came out with that great recombination algorithm and package on GitHub that's made a lot of these calculations a lot easier. So with that, I'll open it up to questions. Thank you.
Got some questions there in the back.
Thank you. It was a great presentation. Did you enforce the, some of the compactness or any other metric in that? I didn't get that part.
That is a great question. I kind of skipped over most of the algorithm stuff, and I'll say that is what's been occupying my time for the last 6 months, is trying to kind of play around with the algorithm, because what these algorithms are frequently used, you kind of set the boundaries that you want to use in terms of compactness or efficiency gap or whatever, what seems reasonable, and then you run these chains to get representative samples. We're kind of trying to explore the widest possible space of redistricting solutions. So I've been playing around with different compactness settings. We're actually trying to also work on the package to allow us to use, so the way the package works, it's a random walk on a graph to generate the different states in this Monte Carlo chain. And we're actually trying to bias it right now using the modularity gap, using flow weights to kind of bias it towards grouping together CBGs that have stronger mobility flow connections between them. So all that to say, we're kind of working on the computational side of how to literally implement that so we don't crash our server, and to kind of explore the widest space of parameters.
A couple related questions. One of them is like, how do you compare the, your algorithm to, like, let's say, community detection such as Louvain or Leiden methods? And also, like, I'll ask the other question too. I see that, like, there are some rigid rectangular boundaries that do not look natural, but this is like what I also see when I do research in similar topic, regionalization. And we often like observe this in any kind of data, like even mobility has nothing to do with county boundaries, but we do capture them. So what do you think about that? How do you explain that?
Yeah. Well, let me take the first part of that question first, if I understand it. So this isn't quite community detection. We're using some community detection metrics, like for modularity. But the thing is, we know how many districts we want. We're not trying to just kind of naively discover in an unsupervised way how many communities there are. We know we have to limit to 8, and we know they have to be equal in population and contiguous. So we have some hard constraints there. And so to initialize any of these algorithms, you actually have to start with an initial map that you kind of then go iteratively changing. So I know that doesn't directly answer your question. In terms of the community detection aspect, that's probably the closest, is so you turn your map of CBGs into a graph, and a lot of these approaches don't use a weighted graph. It's kind of a random walk on a graph. Like I said, what we're trying to do is actually use the weights on those graphs to bias it towards selecting those. So in that sense, there's kind of a community selection bias there in the random spanning tree process when you're making those. So, but it's kind of a mixture of both. So, and can you remind me of your second question? Sorry. Oh, for the bounds. For the bounds of the regions, I suspect they're going to look kind of wild. I mean, this, so the one I had up here, this was just something we kind of, when we were first getting the package going, I'll say I first spent a year trying to code this by hand, a similar algorithm, and the results were terrible. They were not very good at all. So it was not good at exploring the space. So this algorithm is literally trillions of times better, to put it lightly. So, the straight lines we see on here, I suspect they won't look like that when we run the algorithm for longer, but I will let you know when we do the full publication and we get a better sense of the solutions.
Just a quick comment. I think it must be something to do with initialization, I guess, because you said you started off with the current map, right?
Yeah, I would say if anyone's looking for a map to kind of do this random sampling, this algorithm is really great. It's actually after very few, normally these kind of algorithms really struggle with getting away from the initial map, and so you have to redo it with a number of different initial maps. This algorithm is really great at even after 100 iterations, you can't really recognize the original map at all. So it does a really good job of kind of taking these big steps across the state space. So I think in this case, it's just a question of we just needed to run it for longer than we did. Hey there.
I may have missed this in the very beginning, just prior to when you said that when you talked about the geographical approach or the geographical definition of community. And I'm curious as why community versus neighborhood, because you talk about districts and neighborhoods and boundaries and redistricting, but then you use this term community that we can transfer over to the political science realm. And I'm just curious, like I think of like a business community. How would you define that in this sense? It probably would not be the same, but other communities and regions are disconnected geographically potentially. So why that term versus neighborhood or some other geographically defining term?
Sure, that's a great question, and I will answer to the best of my ability. I think part of it's just the bias of the field we're in, because census block groups are frequently, at least I usually hear them called neighborhoods. So that kind of is already occupying that space. You know, when people talk about like those small census units, they're thinking of those as neighborhood level geographic groupings. I'd be curious to hear other people's thoughts on that, but that's what I tend to hear it described as. So when I'm thinking in community, I'm thinking like you have denser community, like communities and a number of neighborhoods that have differing levels of connections, you know, so we can like say that you could look at, and that's why you can generate a bunch of different maps, because like you do have connections between all places, and it's just the degree to which like they're more densely connected than between other places. So when I think of community, I think of the grouping kind of between those nodes of neighborhoods to form a larger kind of a latent structure on top of the neighborhood levels. So I don't know if that answers your question, but that's kind of how I think about it. And Yuhao would probably have some good ideas as well, because he's also in my lab and we do work on this kind of data frequently. So I'd love to talk after them more about it.
All right, thanks. Any other questions? Anything from online? All right, we got one there? Very good. All right, Nick.
I think a partial answer to the question about the straight lines still being visible is how big do some of these census units look in the rural areas? Because I think that some of these block groups are massive in northern Wisconsin, correct?
Yes, for sure. Yeah.
And so the straight lines are still in there because they're county boundaries, which are forced onto the census block groups. So
Yeah,
some of these, you could have a single unit that's covering, you know, a quarter of the map up there. And compared to Milwaukee, where you've got, you know, 10,000 little units down inside that one district.
Yeah, that's a great point. Yeah, I'd like to kind of just emphasize that. So yeah, up here, the census block groups tend to be a lot bigger. Northern Wisconsin, a lot less densely populated. So even though we've, you know, made the line a lot more jagged compared to the existing map, you know, it's still relatively straight. Whereas, right, Milwaukee, you know, looking at the same scale, the census block groups in Milwaukee are much smaller because it's a much more densely populated city. And so, right, the edges are going to look a lot more fuzzy in comparison. So that's a great point.
All right, I think we better close it there. Let's give a round of applause to Jake and all of our speakers. Thank you.